Okay, here we are back again. Just give me a moment to make sure the audio is working. This question is problem number 1130, minimum cost tree from leaves. Double check that the stream is live. Hello. Problem number 11. Nice, very good. We're live. Okay. So let's continue. So I think I'm good to share my screen. I think so. Very good. All right, next. So minimum cost tree from leaves. I'll close the other question. Get this one going. Let's do that. Let that refresh in the meanwhile. So this one we'll see, and then start talking about it. So it says minimum cost tree from leaf values given an array array R of possible positive integers. Consider all binary trees such that each node, has either 0 or 2 children. Okay, positive integers, binary trees. So it's something of it's not complete necessarily. It's every node either is a leaf or it has 2 children. Okay, that's kind of special. The values of R correspond to the values of each leaf in an in-order traversal of the tree. So if we basically, I think it's an in-order traversal is basically going to give you like a left to right across the tree. Kind of going like this sort of thing. Not sure how to describe that exactly. I know that if you had a binary search tree and you performed an in-order traversal, you get this sorted list of elements. That's kind of how I remember it. But if it's not a binary search tree, then it's not necessarily sorted. So I'm not sure how exactly to describe it, but I think it's an in-order traversal, the result of an in-order traversal. Anyway, the values of an array correspond to the values of each leaf in an in-order traversal of the tree. Okay, fair enough. The value of each non-leaf node is equal to the product of the largest leaf value in its left and right subtrees, respectively. Whoa, okay. So there are the leaves. So these are the leaves. Okay, I see. So this is not going to give you the internal nodes of the traversal of the tree. Okay, that's why they emphasize leaf, not the internal nodes. The non-leaf nodes, those are going to be equal to the product of the largest leaf value and its left and right subtrees, respectively. Okay, interesting. Among all possible binary trees considered, return the smallest possible sum of the values of each non-leaf node. It is guaranteed the sum fits into a 32-bit integer. A node is a leaf if and only if it has 0 children. Okay, I'm not sure I fully understand the question. I'm trying to understand here. 6, 2, and 4. Here are 2 possible trees. Output is 32. The first has a non-leaf. Oh, the sum of the non-leaf nodes. Oh, I see. The smallest possible sum of the values of each non-leaf node. Oh, interesting. Okay. Guaranteed the sum fits into a 32-bit integer. Okay, got a lot of outputs. I'm not really sure how to solve it immediately. It's a relatively small number of leaf nodes, which means the non-leaf nodes could be at most, I think, the same size, roughly. In other words, if you had a complete binary tree, that would give you the most non-leaf nodes compared to leaf nodes. And I believe, I could be wrong about that, but I believe that's the case. In which case the bottom level, which is a power of 2, is going to be, you're going to have the depth of the tree, 2 raised to the depth plus 2 raised to the depth minus 1, where 2 raised to the depth is the leaf nodes and 2 raised to the depth minus 1 is the internal nodes. And I think this is generally true also for trees, that the number of internal nodes is proportional to the number of leaf nodes. I want to say you could have at most, I want to say that you can't have more internal nodes than you have leaf nodes. I think that's the case. Your number of internal nodes is bounded by the number of leaf nodes. And exclusively bounded, meaning it's not less than or equal. They're not going to be equal to each other. I think they're never equal to each other. I think the number of internal nodes is always strictly strict. It's a strict bound. It's strictly less than the number of leaf nodes. Which is to say that the number of values that we have to consider is bounded by roughly 80, which is a small number. That's the whole point of that. And the values themselves are relatively small, between 1 and 15 inclusive. Okay, and it's guaranteed that the sum of these things is in a 32-bit signed integer. All right, so this has a kind of a lower submission rate. It's not a bad submission rate, but it has a pretty high acceptance rate. So this should be like on the easier side, I think, this question. It's not really a low rate of submission, but like reasonable. All right, so it's like 5.5 minutes just to kind of read the question, get an idea. Okay, I don't know the solution immediately. I have to really think about this. Of all the possible trees, so basically, yeah, so this sum is 32, this sum is 36. So here you'd want to put 2 and 4 together rather than 6 and 2. I don't really know how I should group these numbers exactly. It seems to me like you've got kind of a lot of different possible trees. It's not obvious how exactly all of these should be calculated. Definitely if you have two, maybe I could do some sort of an inductive argument on like what the possibilities are. With 2 elements, there's certainly only one possibility. It's just 4 times, A times B, and then the product, and that's an internal node, and those are both leaves. All the leaves are given to us already, so we can ignore, those numbers won't be part of the product, I guess. Then if we have 3 nodes, A, B, and C, these are the only 2 trees, which it's going to be A and B as a subtree, and then C, which creates another subtree, or A as a subtree and B and C as another subtree, right? And we can generate the respective values from those. So 6 and 2 gives you 12. 12 times 4 gives you 24. 12 plus 4 times 12, right? And here you get 6 times x plus 2 times 4, which is x. So you get 7 times x, where x is 2 times 4, which is 8. Is that right? No. It is 6 times 8. 6 times 8 is not 24. 6 times 8 is 48. Wait, what is going on here? Why is this 24? What? Wait, why is this 24? Wait a minute. Why are both of these? This is 48 and this is 48. What is going on? What? Oh, excuse me. Oh, okay. Actually, this would be a lot easier. This would be like some kind of a product sum, I think. You could always get the same. Well, you wouldn't always get the same values. You get 48 up here, but you get 12 and 8 there. But anyway, the important part is okay, so I misunderstood the question. The important part is each non-leaf node is equal to the product of the largest leaf value in its left and right subtree respectively. Oh, okay, so the largest value in the left subtree here is 6. Largest in the right is 4. This is 24. Largest in the left is 6. Largest in the right is 4. This is 24 again. Okay, I see. Okay, I'm kind of understanding. So I guess we want basically to like isolate the largest values to get the minimum sum. Yeah, we want the largest values to impact as few internal nodes as possible. So probably we would want basically a tree that just kind of goes straight down, where you have the largest value at the top left, and then it goes down. So left subtree is always just the largest value, largest, second largest, third largest, etc., going down, and then the right subtree is just first largest, second largest, third largest, and so on. That's sort of a sum. I don't know if that's always going to give you the smallest sum. Part of me thinks that is true, but I don't really have a proof for that, why that would be the case. Yeah, well, it just minimizes the number of times you see those particular values. So if you did it that way, you have the largest and then the second largest, and then you have the those two multiplied. Then you have the second largest multiplied again times the next second largest. So you have 1, 2 times 2, 3 plus 1, 2 plus 2 times 3 plus 3 times 4 plus 4 times 5. I guess the indices x of 1 times x of 2 plus x of 2 times x of 3 plus x of 3 times x of 4, etc. I think that gives me the optimal sum. And maybe I'm wrong. Maybe it should be the other way around. Maybe it should be like, well, no. So, like you're always guaranteed that the root that you're going to have exactly what I just described. And the question is, okay, well, how do you get the smallest on the left side and the right side, right? Because that's always going to be the two largest. Like it has to be. How do you get the smallest sum on the left side? How do you get the smallest sum on the right side? Or the smallest sum possible between the left and right side? Well, excuse me, you could have, as the way I was describing it, I mean, you could just have the left side doesn't even have any internal nodes at all. And you just have to consider the right internal nodes. And then you have, okay, well, what's the smallest root value you could have for the right side if there's no left side ever? There's never a left side. That would probably be the two. That's actually guaranteed to always, no matter what you have, to always be the two largest elements multiplied. But if you include the largest element from the left subtree in the right subtree, then it's going to actually be larger. It's not just going to be the second times the second largest times the third largest. It's going to be the first largest times the second largest. So that's already going to be larger as a sum than the previous sum, right? One of the possibilities. So assuming you could actually decrease the sum at every point, then you can actually use a heap to perform this summation. And I wonder if it's true. I don't really have a proof that always works. I'd have to kind of think about it to come up with an inductive proof. Let me lay down for a minute. Let me lay down and think about how this could be done. Yeah, I'll be back. Let me think. I suspect I could prove that the result is can be solved with a greedy algorithm, or the result could be computed with a greedy algorithm, and this could be done in n log n time. But the question is whether or not that greedy algorithm is actually correct. I don't think so. My guess is it's not correct. It's probably not. It's just, if it was, this would be a lot easier, right? Because that would be a very quick, clever way of doing this. A quick and clever way of doing this, but I don't think it's that easy. Probably not. Typically not. Probably not. Yeah, because you could have a left subtree and a right subtree. There's no reason not to have one or the other. Obviously, there's some symmetry involved. Let's say I put the largest leaf node in the left subtree and the second largest leaf node in the right subtree. Well, that would imply that I'm never going to multiply the largest value on the left subtree times any of the leaf nodes in the right subtree, which is probably good, except for the first calculation, right, where it's always going to be that one. I think that's optimal compared to any other possibility because I can put whatever I want in the left subtree or the right subtree for the nodes. Excuse me, this is also assuming I can move these nodes wherever I want. I think I can, actually. I think so. Yeah, the leaves just need to be in a certain order, but that order I could put them in any subtrees, left or right. I'm fairly certain that's the case. It's kind of hard to see that, but I'm pretty sure that's true. So then, okay. Let's say, okay, so let's say I put the two largest elements in the left subtree. Excuse me, and all the other elements in the right subtree. Well, I'm still going to have a similar kind of a thing going on where the internal node and the left subtree are going to be the two largest, and that's it. And the right subtree is going to be all of the, it's just going to be the recursive case without the first two elements, right? Which is exactly the same case that I had with just with two less of the larger elements. Here's a question: Is it ever beneficial to take more than just the largest element and put it? Obviously, it's better. The recursive case is better if I put, as opposed to the second, excluding the second largest or the next second largest. You know, not the largest element, not the largest leaf element. I can if I exclude the largest leaf element, or excuse me, yeah, if I exclude the largest leaf element, then the recursive case is going to be smaller, guaranteed. So I would always put in the left subtree the largest element and not keep it in the right subtree. Always do that. And now the question is, do I do more than one element in that way? I think if I do more than one element, I end up in the same situation where I'm going to the internal nodes that I multiply. I'm going to always end up removing one element at a time into one subtree or another. And if I remove multiple elements into another subtree, well, then those multiplicative products, it's going to be the same thing where as I move further down, I'm just removing one or the other, at most one at a time, or yeah, either at most one at a time or splitting into different like subsets, but each of which still have the same kind of rules. Eventually, it'll get to a point where I'm removing one or two at a time, or yeah, one at a time, I guess. And I still have to calculate the product of the largest values to multiply among those subsets for each value going down anyway. Point being that I think the optimal thing to do is to always remove the largest element at each step. That's what I'm trying to say. That's kind of what I said before, but I'm trying to think of a better way to prove that this is exactly the optimal. Yeah, okay, so let's suppose that I broke this into two different subsets, A and B, and I recursed excuse me, those two subsets. Well, as I said, the optimal thing to do would be clearly optimal would be one subset contains the largest leaf node and the other subset contains the penultimate leaf node. Now, is that better? Is that the way to go? Yes, that is better. Yes, than the alternative, which would be to have the two largest multiplied together. In some it would be better. It would be better than any possibility that includes the two multiplied together again. That number is always larger than the other options. If there was so-called other optimal options, that's always worse. So yeah, you always end up splitting one and one on one side and one on the other. And now another question is, okay, well, I can multiply. So consider consider putting the largest element in the left subtree and the second largest in the right subtree. Now, let's consider any element that I might put in the left subtree. Any element that I might put in the left subtree, the largest is going to be multiplied by let's call that x sub 3, by x sub 1, where x sub 1 is the largest leaf node period, right? So I could do x sub 3 times x sub 1, but or x sub j times x sub 1, but x sub j could also alternatively be multiplied by the next largest to itself. In other words, x sub j minus 1 if these were in sorted order. Could multiply x by j sub j by sort of anything, except I don't have to multiply it by x sub 1. And so it would be better to actually keep x sub j away from really anything that's smaller than x sub 1 would be preferable. So it would be better to keep x sub j actually in set B rather than set A. And since that's every possible node, that would imply that that the left subtree should only have one element, which is x sub 1. Yeah, it's really confusing, I realize, but I'm trying to figure out a way to describe this, a way to explain it. I think maybe this works. I don't know. It's not a solid proof. It just seems to be that way. I don't know what to say about it. It just seems very likely. It just seems to be very likely. How to prove this exactly? Yeah, it's true. Excuse me. Anything that I put in set A as opposed to set B, that would get potentially be multiplied by x sub 1, and so if I have to multiply it by something, has to be combined with some other leaf node at some point, or yeah, some other what do you call that? Yeah, some other node. It would be best if it was combined with not with x sub 1, with the largest. Right. Excuse me, I don't know if this makes sense what I'm describing. I don't know. This is kind of... Yes, has to be paired with something else. Every leaf node is going to be multiplied by some other leaf node, absolutely. True. Is that a round robin? How does that work? If every leaf node is combined with one other leaf node, how many pairs do I have? That means that I have n pairs, right? Every node is paired with one other thing, which makes n pairs, or there's n nodes, so n pairs. And how many, like, that'd be like the number of edges. How many vertices do you have? If those were edges, how many vertices do you have? Well, the number of vertices, or incidence points, let's phrase it that way. Degree, what's the degree of this, if this was a graph? That's what I'm looking for. The degree is going to be 2 times n. That's the important part. The reason why the degree is relevant here is that, actually, I'm not sure why that's relevant. I guess I just want to think about what that is. Yeah, the degree of this graph. Yeah, I guess what I'm trying to say is that it's like a graph of vertices. You can think of it that way. Graph of vertices. And I need n edges, and I'm saying the optimal way to do this is to just draw your edges straight across from the largest straight down to the smallest. Because the other options would be basically if you were to move the edges and have more than one edge coming from one of the nodes. Yeah. Yeah, it's kind of like it's similar to like a minimum spanning tree, where the length of the edge, the weight of the edge, is equal to the product of the values of each of these vertices, the incident vertices. Yeah, and if you were to perturb the spanning tree that I've described, then you'd have like sort of a kink somewhere in there where you'd have some, let's just say like right in the middle, some I and I plus 1, these vertices where, again, these are, let's say, well, they're in sorted order. So let's say I'm sorted in descending order from v sub I to v sub I plus 1, and I've got, normally have that edge there. Well, let's say I remove that edge and I add an edge somewhere else. Well, I have to have, it really could be any other edge involved. I think that's the key. You just have to have some other edge somewhere. But the problem with this is, I think the first thing is that you always are going to use, never mind, this is very confusing. I'm starting to get to so many different, I've kind of moved off into such a strange position there. I'm not really sure how to describe it. Yeah, I don't know if you could just draw any, because if you could draw any edge, then actually maybe it's not the worst thing to consider. Just kind of the problem I'm wondering about now. It's actually true if you had something like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 10 times 1 would be better than like 6 times 5. You actually would want 10 times 1 instead of 6 times 5. Okay, I'm not sure. Maybe that's not that's not quite right. Gee. Excuse me. Excuse me. Wow. Maybe I'm looking at this question the wrong way. Also, by the way, maybe some of the things I'm thinking are not quite, don't quite work that way. Huh. I think I might be able to do this in quadratic time or cubic time. Maybe cubic time is what I want to do. So I could try to do it this way. I could try to split into a left subtree and a right subtree the different leaf nodes. And I would take the largest leaf node on the left, the largest maximum value on the left side, and the plus the times the largest maximum value on the right side. And I would take that product, and then I would recurse, which I probably would want to figure out a way to do. Maybe I do want to do RMQs to get the range maximum queries efficiently. That may not be a bad idea. Okay. Yeah, okay, I could do a sparse table to get the range maximum queries pretty quickly. I think that's fine. I think I need, why do I need to do that? I'm wondering if that actually, if it even matters if I do that or not. Because I end up with some I sub 1, J sub 1, and I sub 2, J sub 2 for the left range and the right range. And that would give me actually 2 parameters to my recursion, memoized recursion, which would mean this is going to be a cubic algorithm, because I would do a quadratic amount of work, memoized work, and then I would do a linear amount of, do that memoized work in a linear amount of space. Fortunately, it's only quadratic memory, so quadratic memory, cubic runtime, and using dynamic programming to support this. Yeah, that could work using, I guess, top-down memoization. So I suppose I could have solved this a lot faster if I just went straight for that. I'm fairly certain that works. Yeah. Excuse me. The base case is just when there are two elements in the consecutive elements. Is it possible for me to DP upwards? Yes, I could start with two elements at a time. That creates some internal leaf node. And then above that, then you have the subtree to the right or the subtree to the left, depending on how things have been done. And I'm kind of falling asleep. Let me put my headset down and just kind of close my eyes for a minute or two. Kind of falling asleep. Oh man. But it is definitely true that oh wow, I'm falling asleep, huh? Whoa. Oh no. Thank you. Sorry. Huh. I think I just fell asleep, but the original idea that I had was just take left to right, take the value I, we'll say, or k, let's say value k at index k. From left to right, let index k be the I guess over some subrange, that's going to be the split point where the elements including k to the right for some I and j, those elements k to j inclusive are going to be the elements present in the right subtree of the elements split from I to j, and the I to k minus 1 is going to be the left elements. Yeah, where k is some element between, well, it could be I. Yeah, it could be I. No. It's got to be for some I greater than or equal to I plus I plus 1, or some k greater than or equal to I plus 1, and less than or equal to j. So between I plus 1 and j inclusive, which is j minus I plus 1, which is j minus I. Okay. Anyway, yeah, then I can split into left and right subtrees, and then I would just, for each of those possibilities, just add the product of the two largest elements on the left side and the right side, and presumably I can use what's that called? A range minimum query to find the minimum of those ranges efficiently. But actually, I don't think it matters, because I can just loop from left to right. I guess I'm going to do a left to right loop anyway for all of the recursive cases. Doesn't make a difference to find the. Actually, maybe it does. Sorry, I'm like falling asleep over here. Trying to think of a way to avoid using a sparse table here. That's kind of the thing. I guess it doesn't really matter. You could just brute force all of the largest values in each, all the maximums in each in quadratic time. You can find that in each range, and just save those values. And the reason why that would be efficient anyway is it's not that efficient, but it's efficient enough. Is because the whole algorithm I have here anyway is going to be quadricubic anyway. It doesn't matter if it's going to be quadratic extra run time to save those quadratic number of steps to get the maximum value in each of those ranges, and then also to get the DP, it's going to be, you can just calculate the largest. You can calculate the largest intervals one at a time, I think. That makes sense. So for 3 elements, what is it? It's going to be the find the size 1 interval, the size 1. It would only take quadratic time. Yeah, I'm definitely like falling asleep over here. Forgive me, those of you who are watching, wondering why I'm like really slow to answer this question. No, I think I do. I think it's fine to do cubic time. Yeah, it's going to be each of the, from left to right first, it's going to be size 1 elements, which I think you just return themselves. Define it that way to just return themselves. And then size 2 elements is going to be the product of the 2 elements, which will both be left and right. Then for size 3, I guess each size I'm going to run through left to right on each one and take the maximum of the left. How do you say this? Like for 3 elements, I could do 1 on the left side and 2 on the left side, which gives me 1 on the left side, 2 on the right side, 2 on the left side, 1 on the right side, and those would give me. There's a sum associated with those 2. The sum is, if it's 1 element, is a 0. If it's 2 elements, it's going to be the basically recursive case. So I think for a given I and j, I could just return whatever value is there, right? And so for a given like I to I plus k, I'm going to loop over each k values. I think it's going to be, excuse me, perform a loop from k equals 0 to, or yeah, I from I to I plus k, or I to I plus j, we'll do it that way. Where k loops from 0 to, actually I think k should be 1 to j. Yeah, k loops from 1 to j. Where I think you have the left side is I to k minus 1, and the right side is k to j, I plus j. Yes. And you'd get the maximums of those 2. So you have one, somewhere you have the maximums. Those 2 multiply together plus the dp of the left side plus the right side dp. Yeah. Which single element, the dp is going to be 0 by definition. 2 elements, it's going to be it's going to be just the product, right? Because the left side and the right side will both be 0, but the product will be non-zero. It's not defined when the product doesn't exist, when it's just one element. That's a little bit confusing. Yes. Yeah, that's what you could do. Use DP to do this, to go bottom up instead of go top down. Top down memorization, you could use DP to go bottom up. Ooh, excuse me. Oh, that took me a really long time to get through that, to explain that. Yes, I think you just have to specify from k equals 2 upwards, and then when I is 0, from I to I plus j, the largest value for j is going to be excuse me. Oh my goodness. I think I should do it the other way around, where I and I plus k is the where k is always at least 1. Where k plus 1 is the size of the interval, and then j is just from I plus 1 to I plus k. And so the size of the interval is going to be k plus 1, and then we're looping from the size of the interval being 2, so k plus 1 equals 2 means k is 1, up to and including k plus 1 equals n, which means that k is less than or equal to n minus 1. Or just k is less than n. K equals 1 to k is less than n. Okay. Well, that's confusing. That's confusing. G. That would be a triple loop. Exactly what I was saying. That would give me a triple loop. Kind of wish I was able to think that through a little bit faster. Oh man, I think I need a break after that. Jeez. G. I don't know what to say. Excuse me. Yeah, I'm gonna go with the. Oh my goodness, what happened? It was an hour I spent. Oh, that's not good. Not good to have spent an hour thinking about this, talking about it. It's okay, but it's not great. So yeah, I think I could do this cubic time using a DP. There may be a faster way to do it, but I think this is reasonable. And I'll kind of explain what this would look like. So this is going to be max val n by n. Let's do constant n is array.size. Let's do for each I is 0, I is less than n, increment I. Fill this, just initialize these values. Okay. The maximum element. And so then I want to do a double loop from int equal I equals 0, I is less than n, increment I. And then this is going to be from int j equals I to j is less than n, increment j. And say largest or best equals array of I. Best equals standard max of array of best and array of j. And then at the end, I'm going to write max val of I. No. Max val of ij is equal to the best. Okay. Yeah. Which means this doesn't actually need to happen here. Actually, I should do it that way. Yeah, no, that's fine. This is going to be like a partial array type of a thing. In other words, this is sort of a triangular array. Like it doesn't, I'm not actually going to write a maximum value for j and I when j is less than I, right? Yeah, that's fine. Okay, I could do it that way. Now I can do a triple loop, as I was suggesting, using a DP. DP of n by n by n, really just n by n, same thing, similar thing. And this is going to be dp of I. Then I return, this is the smallest value we're looking for. Yeah, the smallest value. This dp is going to be from 0 to n minus 1, of course. And as I was suggesting, it's going to be from k is 1 to k is less than n. Yeah. So it's going to be I and I plus k, right? Int I is 0. I plus k is less than n. J. The way it works is you've got j is going to start at I plus 1. And that's going to go to I plus k. So the range is going to be I to I plus k, right? Left to right. We're going to kind of do each of those ranges for a certain each value k. And I plus k has to be less than or equal to n minus 1, or I plus k is less than n. And then j could go all the way to I plus k, right? Okay. Now the way this works is for each value of I, each value of j, we're going to update starting from k is 1. The first thing to say is that dp of I is 0, I is less than n, increment I, dp of I is just 0. That's important. Then we're going to say for k is 1, we have the best value. This is going to be the smallest value. We'll start off at some maximal, which I think is just going to be it's basically the sum fits in a 32-bit integer. I mean, it could be also just an optional. That's maybe the easiest way to do it, is to use a sentinel this way. All right, we'll just say best. And we're going to say if best hasn't been set yet, not best, or, and ultimately this is going to be, we're going to say dp of I and I plus k is going to be set to best. That's the key here. What this is going to look like if the best hasn't been set yet, or, and there's this value, so constant val, we'll set best equal to this value. Or best is less, or val is less than best. right? If we found a way to improve, then we'll use that. So this is going to be, it's dp of I to j plus dp of j to I plus k. That's the key. And we'll say r is I plus k, because it doesn't change there. Oh, no, it does change there. No, that's I plus k. R is could be the right bound, or is I plus k. This doesn't change here. Yes. Okay. There's also this max val times max val of I and j and R. Okay. Yes. Right. It's something like this. That's going to be the best value that I get for a given I and j, looping, where for certain I and k, I'm looping left to right and looking at all those sections of that size, and then I split some j splits that into two smaller groups, and for each one there's sort of a left to right sequence, and this is what you end up with. You end up with the dp of I and j on the left side, dp of j and r on the right side. It should be j plus 1 actually, and or rather, this is j minus 1. It's more accurate. That's what it should be. Yeah, j minus 1. Right. That's it. That's why I have the plus 1 here, is because you're going to subtract 1 here. That's why I have it there. Yeah, a little bit confusing. As I said, I was kind of having a hard time explaining this, kind of thinking it through in my mind. It's like not the most obvious. Oh, excuse me. Oh, okay. I think that goes here. Yeah, okay. So it's going to be for each k and each I. I'm going to write all these values here. Yeah. Okay. Interesting. It's something like this. It's something like this. Not too obvious. It's not too obvious how to do this. And I think this value should actually be here. Yeah. I think so. How am I doing on time? Okay. Let me try a few more cases. I think it's something like this. Something like this. Let's try these different possibilities. Excuse me. Okay, this seems to be correct. I don't really have a good explanation for this. Try some random things. Maybe I could just generate some test cases. Maybe I should do that. Some random test cases, do a little bit of fuzzing. I don't know if I need to. It feels like I should be able to prove that this is right. My intuition says this is correct, but it's definitely not like obvious how to explain this or like how to prove that this is right. I think this is right. I'm gonna go for it. It could be wrong, but I think it might be right. Okay, got it. Nice. Very good. And it's pretty fast. All right, I'm gonna submit this 4 more times. I'll try to explain it, synopsis at the end. Yeah, basic DP kind of works nicely here. Doesn't give me 100%, but it gets me pretty close. 3 milliseconds is not the worst. I think if I resubmit it a few more times, I can get 100%, get 0 milliseconds. 1, 2, 3, 4, 5. So if you like this video, give it a like and subscribe for more. 1, 2, 3, 4, 5. Yeah, I think if I made this a little bit more efficient, I can get this to be. I don't actually know if I need this line, by the way. I don't think I do. I definitely don't need that. I don't think I need this either. Yeah, I don't think I need this either. I don't think I need either of these. Let's see if it's still correct. It might be. Yeah, I don't actually need that. Fairly certain. Yeah, it doesn't make it faster. 1, 2, 3, 4, 5. Not much. But it's probably better to just do that anyway. Yeah, it's not the fastest solution. It's pretty fast, but it could be faster, I think. Yeah, I mean, I don't know. Yeah, it's doing quite a bit of like lookups and things like that. I could maybe use the sentinel value here. Maybe that'll make it faster. And just do. I don't think this is much better. This might actually be slower. Could try it though. See how fast it goes. Maybe? I don't know. Yeah, it's slower. Or it's probably about as fast. Not much faster. Can get rid of these lines. Use it slightly, code it slightly differently. I don't know. No, yeah, it doesn't. It's just a little on the slower side, which is surprising, quite frankly. Yeah, I could reduce the amount of work that it does here. This could be turned into a. This could be turned into an LMQ. Like I could do a what's that called? I could do not LMQ. I can do a sparse tree here. Could make a sparse tree here, and actually reduce the total amount of calculation done here. But this isn't that much. I mean, this is really where the bulk of the things are, the calculations. Excuse me. Yeah, I could do. Could do this way. That's another way of doing it. This might reduce a little bit of the calculation that's happening. Maybe that's something good. I could try that one. Let's see. Sure. Oh, this is also R. Okay. Just trying to reduce the total number of operations being run in the loop. Maybe that's good. No, it doesn't really matter. Doesn't really. I don't know what to say. Yeah, okay. It would have been good if I basically figured this out faster. This is a reasonable solution. This is reasonable. You can come up with this pretty quick too. If you just if you go for like the first thing off the bat, it would be pretty quick if I figure this out. To do it this way. This is a cubic time solution with a quadratic amount of extra memory, and not really not too fast, not too slow either. It's not the fastest solution. I can check some of the other solutions to see which ones are faster. Kind of disappointing it's not the fastest. It's reasonable. Oh, there we go, got it. Hey, hell victory. Got it, yay, hey, got there. Yes, and hey. Sometimes I say yes and hey and I end up with yay, which I don't think yay is like not the most masculine thing to say. There we go. Okay, I just had to keep trying, I guess. Keep rolling until I get 100%. All right. Satisfied. Very good. All right. So thank you for watching. I'll stop there. Again, if you like the video, give it a like and subscribe for more videos like this. It took me a long time. It really took me a long time. I probably should have went straight for the DP. I didn't think about it. I probably should have done that. It's fast enough. It's fast. Yeah, I'll stop there. So I think I'm gonna take a break too. I don't know what to say about that. I didn't need to take so long. I didn't need to take so long with that. That wasn't that hard. Just kind of got stuck on it for some time. Yeah, I'm gonna take a break. Maybe take a break for an hour or two. Maybe just rest, I think. I don't know. So yeah, thanks for watching. Take care. Have a good rest of your night, rest of your day. Just check chat before I go. Oops. Yeah, okay. All right.